So at this point, I think it's pretty safe to say that we shouldn't think anymore about including an interactive effect between grants and rank. But I do want to talk about how we should start to think about incorporating additional variables into our model, and specifically things that may affect the rank that someone is able to achieve based on potential institutional hurdles that they see that would also impact their ability to get grants and thus their salary, right? So there's something that's still lurking, and there's probably many variables that are lurking that are pre-treatment to our predictors as well as our outcome that might explain that covariation away. If we don't include that in our model, then we may not be actually explaining the true data generating process that we think we're explaining. So let's just add gender in. And what we can see here is that on average, in comparison to women of similar rank and that have similar grants, holding those variables constant, men on average earn about $4,300 more than women. At least that's what we're getting from that estimated coefficient in our regression model. Now, this is an additive effect, of course, and we may be interested in whether or not the effect of grants or rank is altered by gender. And I think one quick way of looking at this is, again, looking at our data visually. And so we're going to inspect it using a lattice plot, which, again, is just going to essentially be a scatter plot that's broken up into different columns or rows based on these categorical predictors. And I'll show you how to do that, one in R and what that looks like. And so here, qplot is just opening up a scatter plot. And essentially we are doing facets by gender as well as rank code. So male, female, associate, assistant, full. And we're going to look at the relationship then between grants and salary between these different categories. And when we do that, we can see that there really actually doesn't seem to be a differential effect of grants by male or female, nor necessarily between full, assistant, and associate, in the sense that there's an interactive effect. Now, there could be an on average effect that men make more money, so the intercept of this relationship may be higher, but it doesn't seem as if the slope is steeper for men versus women. So at this point, you're probably wondering, at what point do we toss in the towel and think that there are no longer benefits of comparing two groups together? We should actually use slopes that are different, or we should just use a parallel line. And I think the best way to do this is by including that interaction and then using tests that we're familiar with to compare groups, like a partial F-test. And if there's constant variance within the groups and across the groups, we're going to have a better estimate for our actual sample variance, our sigma squared, when we pool the data. And I think that makes sense because if we had, again, differing effects, we'd have different variation between these two groups. And if the variation is essentially the same between these two groups, then there isn't too much reason for us to want to model them separately. And another benefit too of having a pooled model where we don't differentiate the effect by group is that we are inherently going to have more degrees of freedom because we have more observations within that group. And so the bounds of uncertainty that we have around our beta estimates are inherently going to be smaller. And so it's a weird effect to think about, but when we include in an interaction effect, we may actually be inducing more uncertainty around our estimates just because we have fewer number of observations within each group. So again, if we test to see if that interaction is indeed different from zero, that it should exist, the slopes are separate between the groups, we again can just do this with a simple t-test And if there is a significant interaction, then the effect of our covariate X, in this case, grants in the previous example, on the response, salaries, is different for different values of our D, our group, so for rank. And we were unable to reject the null hypothesis that our beta 3 was in fact equal to 0. Now, if there is no significant interaction, then we can then test if there are two separate parallel lines for the group, or if one is sufficient to describe the data. So again, remember, the first step that we did was we just looked at our beta 3, doing a simple t-test, and then when we also were looking at multiple categories, we then did a subset regression where we did not include the dummy variables and interactions, and then we also included a full model, which did. We compare the two, and that is essentially what we're talking about with regard to the two separate parallel lines for the two groups, or three. As always, when you have dummy variables in your regression model, you need to keep in mind what coding scheme was used, because this is inherently going to impact the way that you interpret those covariates. So you need to remember which variable is associated with 1 and which is with 0, because that's going to inform what your baseline category is and what covariates and coefficients are going to be x'd out of your fitted regression line. Now remember, numerous covariates can be used in conjunction with a dummy variable, though we only show one covariate in this example. We started to do that with regard to gender, so you could see that we even had multiple dummy variables in our regression. It doesn't matter how many dummy variables we have per se, though I would say that adding more variables inherently is going to reduce the efficiency of your model as well as the fit. And so that's something we'll get into later. We want to maintain a parsimonious model, but for right now, there's nothing with regard to the calculations that make it such that we can't have numerous different dummy variables within the same model. And as just a brief point of review, today we talked about interaction models, and in the previous module we talked about additive models. Finally, as a rule of thumb, if you ever have an interaction term between two variables, you must include the constituent or main effects for those variables. So if your interaction is in the model, you should be including and looking at the separate effect of your x and the separate effect of your dummy variable. Then when you're making an inference on whether or not that interaction is significant, we do a simple t-test and then we proceed from there. If there is a significant interaction, we don't really consider the tests for the main effects. We're really interested in the significant effect, right? Because there are clearly different reactions or different effects of our x on our y given different groupings. And if there isn't a significant interaction, we mostly then are interested in the main effects, right? We're interested in the actual additive effects of our covariates.